Hey everyone. Chapter 8 is usually a fan favorite, electron configurations. The rules are going to seem a little daunting at first in how we distribute electrons into the specific atomic orbitals within an atom, but once you get the hang of it, students tend to really like this chapter. And so, if you've ever looked at the periodic table, you might be wondering why it's arranged how it is. Why don't they just put it in a rectangle that fits on paper a lot better? But it's arranged in a very specific way, and it has to do with the electron configurations for each of the atoms. And you're going to find that use of the periodic table is going to help you to remember how to fill the atomic orbitals with the electrons. And for the entirety of this chapter, I highly recommend that you have a blank periodic table in front of you to take notes on. And so we'll talk about first how to distribute the electrons within an atom. We already know how to identify how many electrons an atom has. Remember, for a neutral atom, the number of protons equals the number of electrons. And so if you know the atomic number, then you know how many electrons the atom has. And so where do we put the electrons, or where does the atom put the electrons? It's going to follow the Aufbau principle, which means to build up. Electrons are always going to go into the lowest energy sublevel that is available. It's shown on this energy diagram over here to the left, where we have the lowest energy down here, and it increases in energy as we go up. We also have the energy sublevels listed here. Yes, you're going to have to know how to fill the energy sublevels, but the periodic table is going to make this very logical and not exactly a memorization task. One thing you will have to know is how many orbitals there are in each type of sublevel and the maximum number of electrons that you can put into that sublevel. And so we've already talked about the different types of orbitals. Remember, it's represented by the quantum number L. There's S, P, D, and F. In any S sublevel, there's one possible orbital because there's only one possible orientation. And if we can put a maximum of 2 electrons into an atomic orbital, that means in an S sublevel, you can have a maximum of 2 electrons. In a p sublevel, there are 3 possible orientations, or 3 possible orbitals, and if you can put 2 electrons into each orbital, that means in any p sublevel you can put 6 electrons. In a d sublevel, there are 5 orientations, or 5 orbitals, and so we can fit a maximum of 10 electrons into any d sublevel. And for an f sublevel, there's 7 orbitals, 7 times 2, we can put 14. And you're going to notice that certain regions of the periodic table, the width of those, the width of the elements, is going to correspond to 2, 6, 10, and 14. I'll elaborate when we get there. And so for instance, a neutral oxygen atom is atomic number 8, so it has 8 electrons in it, and 2 of the electrons will go into the first available energy level, which is the 1s sublevel. We'll put 2 electrons into the 2s sublevel because that's the next lowest energy level available. And then finally, we have 4 left, and so we can put those into the 2p sublevel, which is the next lowest energy level that's available. Remember, we can fit a maximum of 6 into the p sublevel, but we only have 4, so we'll put all 4 of them into there. And the way we represent that electron distribution, or one way, is with an electron configuration shown here. We would say 1s2, 2s2, 2p4, indicating that in the 1s sublevel, which is spherically shaped, there are 2 electrons. In the 2s sublevel, remember this one is on the second energy level, it is also spherically shaped, there are 2 electrons. And then in the 2p sublevel, there are 4 electrons. And so there are 2 major ways that we're going to represent these electron distributions. The main way is going to be using text with the electron configuration. Another way is to draw orbital diagrams. The electron configuration is a string of text where you have a number and a letter, and then this superscripted number. This first number represents the energy level. How far away is that electron from the nucleus? Next, we have the letter, which represents the quantum number L, the sublevels, and that can be S, P, D, or F. And then the superscripted number is the number of electrons that are in that sublevel. And so, again, for the neutral oxygen atom, we have 1s2, so N, L, superscript, 1s2, 2s2, 2p4. An orbital diagram has each electron represented with a single arrow. So each arrow equals 1 electron. And we can put 2 electrons into any given orbital. And then we represent the orbitals with some sort of geometric shape. And in this textbook, they use boxes as the geometric shape, but you might also see just lines or circle. Each box represents an orbital, and each arrow represents an electron. Each electron has to be facing up or down, and that corresponds to its spin. Positive 1/2 is an up arrow, negative 1/2 is a down arrow. And in the 1s orbital, we've got 2 electrons, and they have to have opposite spins according to the Pauli exclusion principle. So we've got one facing up and one facing down to represent the 2 electrons in that 1s energy level. In the 2s energy level, we've got 2 electrons, one up, one down. And then in the 2p sublevel, we draw 3 boxes to represent the 3 possible orbitals that are on any p sublevel. And then we distribute those 4 electrons as far apart from each other as possible. And so in the first box, there's one up and one down. And in the remaining 2 boxes, there's only 1 electron, and each of them has to be facing up by convention. And in all of these orbital diagrams, you can either write them horizontally, but they have to go in order of lowest energy to highest energy. You could also write them vertically, or Alex is going to have you write them diagonally. But in all cases, you're going from lowest energy to highest energy. Some of you may be wondering why I put 2 electrons in this box and 1 in each of the others. Well, there's a rule that dictates that, and it has to do with energy, as does pretty much everything in chemistry. And so Hund's rule states that when orbitals of equal energy are available, the electron configuration of the lowest energy has the maximum number of unpaired electrons. All right, so let's break down what that means. If we have a nitrogen and there are 7 electrons in it, which there are in a neutral nitrogen atom, the correct electron configuration would be 1s2, 2s2, 2p3. So there are 3 electrons in that 2p sublevel. And there are multiple ways that you could distribute those 3 arrows into those 3 boxes. The correct way would be this one here on the left, where there are 1, 2, 3. There's 1 electron in each of the 3 orbitals, and by convention, it has to be facing upwards. And this represents the maximum number of unpaired electrons. We have 1, 2, 3 unpaired electrons. If you had drawn the electron configuration over here on the right, it would technically be incorrect because it's not going to be the most stable. It would represent one that is of higher energy. And so having this pair of electrons here and having an empty orbital over here is not the most favorable situation energetically. And we can see that from there being only 1 unpaired electron versus 3 unpaired electrons. And the way I always follow Hund's rule is I just always start with putting up arrows in each available orbital first. And then if I have more than 3 in a p sublevel, then I'll go around and start pairing them up. When you're drawing orbital diagrams, it's important to draw all of the possible orbitals that are available in a sublevel. For s sublevels, there's only 1 possible orbital, so you always draw 1 box for an s sublevel. For a p sublevel, you're always going to draw 3 boxes because there are 3 possible orbitals on any p sublevel. So even if there is only 1 electron in that p sublevel, you still have to draw all 3 boxes to represent the possible orbitals that are available of equal energy. For a d sublevel, you always draw 5 boxes to represent the 5 possible orbitals. And for f sublevels, you're always going to draw the 7 possible boxes for the 7 possible orbitals that the electrons can go. All right, memorizing that order. I promised you that it was a lot easier to remember than just straight up memorization, and I'm going to show you how you can use the periodic table to remember the order that you fill the electrons in, or what energy levels get filled first. It's easy at first, but once we start getting into the D and F blocks, it gets a little bit confusing. But the way the periodic table is laid out is very logical. And so if you can remember where the blocks are, which I'm going to show you here, you can memorize the order. And so on the left, the first 2 columns here represent the S block. And so the number or the energy level corresponds to the period number. So this first row here, that's 1s. And then here we have 2s, 3s. Notice 3s corresponds to period 3. And it just goes in order from 1 through 7. And you'll notice that it's 2 wide, and if you remember, you can fit a maximum of 2 electrons into any s sublevel. And so in the first position here, that means there's 1 electron in the 2s sublevel. This second position, that means there are 2 electrons in the 2s sublevel. On the other side of the main group elements, we have what's called the p block. If you remember, there are 6 possible electrons that can go into any p sublevel, and if you count the number of atoms in this p block, there are 1, 2, 3, 4, 5, 6. And so it is 6 wide to represent the 6 electrons that can go in there. The energy level of the p block also corresponds to the period number. So the 2p sublevel is in row 2 in this p block over here. It goes in order from 2, 3, 4, 5, 6, 7. There is no such thing as a 1p orbital. Next, we're going to go to the d block. There's the transition elements. Of course, they're going to ruin the pattern that you think you've picked up on. The lowest possible energy d block is the 3d block. And the 3d block appears in period 4. And so you have to remember to subtract 1 from the period number. So it goes from 4s to 3d, and then it goes to 4p. And that's the correct order of energy. And if you remember, there are 10 possible electrons that you can fit into any given d block, or any d sublevel. And if you count the number of atoms in this block right here, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so you can remember it that way. And so in the 4th period, we have 3d, and then 4d, 5d, and 6d. Finally, the F block, these intertransition elements that we never really talk about here. Remember, you can fit 14 possible electrons into an F sublevel, and if you go ahead and count how many elements wide these lanthanides and actinide series are, it's 14. Another thing you have to remember here, in period 6, that corresponds to 4F. So for the F block, you have to subtract 2 from the period number to get the energy level. And then to fill the sublevels, the order that you go in, you just read from left to right. You go 1s, then 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, and so on. And so that corresponds to the order that I have given you in the previous slide. So if you can remember where everything is on the periodic table, or remember these blocks and numbers, you can remember the order filling. Another way of remembering the sublevel filling order, this is not my preferred method, but if this is something that works for you and helps you to remember it, I wanted to show it to you. What you can do, you can organize 1 through 7 in a column, and those correspond to the S sublevel. And then you go from 2 to 7 for the P sublevel. Remember, there's no such thing as a 1p orbital. And for D, it starts at energy level 3. You go from 3 to 6, and 4 and 5 for F. And then you just draw diagonal lines through them, and that represents the order of filling. So first you do 1s, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d. So that's where it starts to get a little squirrely. You go from 4s to 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p. And so that represents the order that you fill them in. Let's start looking at the electron configurations for elements in each individual period. So we'll start with period 1, which is the easiest. There's only 2 elements, hydrogen and helium. And remember, helium is still technically part of the S block, even though it's over here on the right. And so hydrogen, a neutral hydrogen atom, has 1 electron in it. And so that 1 electron will go into the lowest possible energy level, the 1s sublevel. And so the electron configuration for hydrogen is just 1s1. If you were to draw the orbital diagram, you would draw a single box representing that 1s orbital and put an up arrow in it to represent that 1 electron. Helium is in position 2 in the first energy level of the S block. So there are 2 electrons in that energy level. And the electron configuration would be 1s2. To draw the orbital diagram, we would draw a single box to represent that 1 orbital, 1 electron up, 1 facing down. For period 2, we add a p block. And so remember, there's the S block and the p block over on the right. And so we're going from lithium to neon. Lithium is in position 1 of the S block. And so there is 1 electron in that 2s sublevel. And so the electron configuration, the highest energy electron would be that 2s1, and any sublevel that comes before it is going to be assumed to be completely full, and it is. So lithium has 3 electrons in its electron configuration, 1s2, 2s1. And here's the corresponding orbital diagram. Even though the 2p sublevel exists, since there are no electrons in it, you do not have to draw it. Next, we would go to beryllium, which is in position number 2. So there are 2 electrons in the 2s sublevel. Anything that comes before it is completely full. So beryllium, 1s2, 2s2. Next is boron. We move into the p block of the second energy level. Boron is in position 1, so the highest energy electron is in the 2p1. We have 1s2, 2s2, 2p1. And as you move across, you're adding a single electron to that electron configuration. So 2p1, 2p2, 2p3, 2p4, 2p5, and 2p6. And you'll notice that the position it is on the periodic table corresponds to that last superscripted number. So fluorine is in position 5 on the p block, 1, 2, 3, 4, 5. And so that corresponds to 2p5. So that's one way you can simplify writing your electron configurations. Period 3 is very similar to period 2, it's just one energy level higher. We have a 3s sublevel and we have a 3p sublevel. And as you move across the period, you add an electron. Once the 3s sublevel is full, you move to 3p and add electrons until you hit 3p6 at argon, which represents a completely full 3p sublevel. And you may have noticed that the electron configuration or the orbital diagram is completely filled with electrons. So the highest energy sublevel that is available is completely filled with electrons here. And that has a lot to do with why these noble gases are in fact unreactive. If you try to add an electron to argon, so if it tries to accept an electron, there's nowhere to put it. It would have to add an additional energy level. So that is not energetically preferable for argon to do. If it tries to give away an electron, then it doesn't have a completely filled sublevel, and that's actually going to reduce the stability of the element as well. So having a completely filled outer energy level is what relates to the stability of those noble gases. All right, so let's do a few examples. If I were to ask you to write the full electron configuration and draw the orbital diagram for a neutral magnesium atom, that means magnesium has not given away or accepted any electrons, just a neutral atom all by itself. You would look to the periodic table to see how many electrons you need to represent. So a neutral magnesium atom has 12 protons and 12 electrons. So we need to write an electron configuration for 12 electrons. And if you remember the blocks on the periodic table, you'll notice that magnesium is in the S block in period 3 in position number 2. So the highest energy electrons are going to be 3s2. And any energy level that comes before 3s2 is going to be completely filled with electrons. Now, which energy levels come before 3s2? 2p, 2s, and 1s all come before there. So let's fill them. We have 1s2, 2s2, 2p6, 3s2. And so this represents the electron configuration for a neutral magnesium atom. One good idea is to double check that the number of electrons you have represented in your electron configuration represents how many you intended to display. We intended to display 12, and if you add up these superscripts right here, 2 plus 2 plus 6 plus 2, we have 12 electrons represented here. Next, we're going to draw the orbital diagrams, and so we need to draw the geometric shapes for each of these sublevels. And remember, for any S sublevel, we draw one box. And how many do we draw for any P sublevel, regardless of the number of electrons that are in it? We're going to draw 3 boxes. So 1 box for each of the S, 3 boxes for each P sublevel that has electrons in it. And then we fill them. There are 2 electrons in the 1s, so we put an up arrow and a down arrow in the 1s. There are 2 in the 2s, so 1 up, 1 down. 2p is completely filled with electrons, but I've made it a habit to fill the up arrows first. So put an up arrow in each box first and then go back around and put a down arrow. This is going to force me to follow Hund's rule when I have a partially filled p sublevel. So I have 1, 2, 3, 4, 5, 6. And then in 3s sublevel, we put 1 up and 1 down. So this represents the orbital diagram for a magnesium atom, and I've written them in order from lowest energy to highest energy. Now Alex is going to have you draw orbital diagrams, and the logic for doing it is exactly the same. The only difference is you have to draw it diagonally. You're still going in order from lowest energy, 1s, to highest energy, but you're going in a diagonal line. So 1s is going to be here. The next highest will be 2s, so you go up and over. 2p is a little bit higher than 2s, so it's going to be above that, and we're going to draw 3 boxes just like we did here. And then the 3s is the highest energy level. So remember, you go in order of lowest energy to highest energy. Let's do another example. A neutral phosphorus atom. So you got to find phosphorus. It's right here. You'll remember that this represents the P block, and it's in energy level 3 because it's in period 3. And so it's in position number 3 as well. So lots of 3's here. So we have 1, 2, 3. It's in position number 3, meaning the highest energy electrons are going to be 3p3. And so any sublevel that comes before 3p3 must be completely filled with electrons. That includes 3s, 2p, 2s, and 1s. So when we draw the electron configuration, or write the electron configuration for phosphorus, 1s2, 2s2, 2p6, 3s2, 3p1, 2, 3. And so this represents the electron configuration for a phosphorus atom. If we're going to draw the orbital diagram, the logic is going to be the same as it was for the last example. We need to draw boxes for each of the sublevels that are represented that have electrons in them. So 1s, 2s, and 3s will all get 1 box, and each of these p sublevels here are going to get 3 boxes. And so we'll go ahead and fill them. 1, 2 in the 1s, 1, 2 in the 2s. 2p is completely filled. I still like to go in this order to follow Hund's rule. 3s is completely filled. And now we only have 3 electrons in this p sublevel, so it's really important the way we display them. We start with up arrows, so we'll do 1 up arrow in each box first. 1, 2, 3, and that represents all 3 of the electrons in that 3p sublevel. So this would be the correct orbital diagram. Again, Alex is going to want you to draw it diagonally, but you'll notice it's analogous to the one I've drawn here horizontally. It still goes in order of lowest energy to highest energy at the top here. And period 4 is a little bit different because now we've introduced the D block. And of course, the transition elements always ruin whatever patterns you think you have down. And so just as a reminder, in period 4, this is the 4s block. This is 3d, so you have to subtract 1 from the period number. So 3d followed by 4p. So in period 4, specifically in the D block, there are a couple of exceptions to the filling orders. The main group elements are just like all of the other periods that we've talked about, where you have 4s1, then 4s2, and then down here, once we get to gallium, it's 4p1, 4p2, 4p3, 4, 5, and 6. However, with the D block, you're going to go in order at first, starting with scandium. We have 3d1, so we go 1, 2, 3. Next, you would expect it to be 3d4. However, chromium has this weird exception. It would prefer to have 5 electrons, so 1 in each of the D orbitals, and 1 in the 4s block. And so its electron configuration, we have up through 3p6, then it goes to 4s1. It's essentially taking 1 electron out of 4s1 and giving it to the 3d sublevel. So for chromium, it's 4s1, 3d5. Then, once we move on to manganese, the filling order returns to normal, 4s2, 3d5, and then 6, 7, 8. Then you would expect 9 to be next. Copper is the next exception to this rule. Copper would prefer to have 10 electrons, so 2 in each of those 5 orbitals, and only 1 in the 4s orbital. So it borrows 1 from the 4s and puts it into 3d to give the electron configuration, or the higher energy ones, as 4s1, 3d10. Once we move to zinc, the electron order returns to normal, 4s2, 3d10. Then we move on to the P block, and then it goes in order of 1 through 6. And so chromium group and the copper group are the ones with the exceptions. And yes, you are going to have to be familiar with those exceptions. And so the element directly underneath of chromium, which is molybdenum, is going to have the exact same exception, just one energy level higher than chromium. In copper, there are two elements right underneath of it that have these same exceptions. So silver and gold will have the same weird pattern filling, where there'll just be one electron in the s orbital and 10 in that d sublevel. So let's do a couple of examples from Alex. Write the ground state electron configuration for a neutral atom of each element. Ground state is just means that all of the electrons are in the lowest possible energy levels. This has been a term that's been implied in all of the electron configurations I've been showing you so far. So don't be thrown off by this terminology, just write it as normal. The important part of it is that it's a neutral atom, so it's not an ion, it has not yet gained or lost any electrons, just the neutral atom. All right, so for nickel, we're going to find nickel. It's in the transition block here. It's in this 3D sublevel, and if you count the positions, it's in position number 8. And so 3D8 would be the highest energy level, and anything that comes before it is assumed to be completely filled. And then when you're in the D block, don't forget to check for those weird elements that sort of break the pattern. And remember, those weird ones are chromium, so position number 4, and copper, position number 9. Since nickel's not in that position, we can assume that it's going to fill in order like we're used to. So 1s, 2, 2s2, 2p6, 3s2, 3p6, 4s2 comes next, and then 3d, position number 8, so 3d8. This represents the full electron configuration for nickel. In these questions in Alex, if it does not specify full or condensed, you may use either. We haven't yet talked about the condensed electron configurations, and I'll talk about those on the next slide. This is a lot to write out, and you have to get it exactly correct in order to get the answer correct, and there's a lot of room for error there. And so we have condensed electron configurations to make writing them a little bit easier. And what you do is you take the noble gas from the previous period and any sublevel that's different from the from the full electron configuration, we write it after that. I'll explain in more detail on the next slide, but this would also be an acceptable answer for this question. Either one would be correct. Let's move on to copper. Copper, right here, that's position number 9, so that's one of the exceptions to the rule. And remember, the exception to the rule, it's in position number 9, but there are going to be 10 electrons in the D block and only 1 electron in that S block that comes right before it. So we're going to fill everything else like normal that comes before 4s. So 1s2, 2s2, 2p6, 3s2, 3p6. Finally, because it's in position number 9, and that's an exception to the rule, we have 4s1, 3d10. And so this would be the full electron configuration for a neutral copper atom. If you were going to write the condensed electron configuration, you would write argon in brackets and then 4s1, 3d10 to indicate what is different between argon and copper. So let me explain these condensed electron configurations in detail. Some of you are looking at the condensed and want to write that because it's a lot shorter and there's less room for error, and I agree with you. So the full electron configurations are what we've been writing so far, and the condensed are significantly shorter. And so the way these condensed electron configurations work, you find the atom that you want to write the electron configuration for. In this case, we have calcium. And then you go to the previous period and you find the noble gas in that period. So calcium is an energy level 4, or period 4. Argon is the noble gas in the previous period. And so what we do is we put argon in brackets, and what's represented by that is the electron configuration for argon. So between 1s2 and 3p6 is completely filled. You'll notice that that is in common with calcium. And the difference between calcium and argon is that calcium has 2 electrons in that 4s sublevel. And so to correctly represent calcium, we write argon in brackets, which represents all of this, and 4s2 after it to indicate the 2 electrons in that 4s energy level. So you can do that with any of the elements. You put the noble gas from the previous period in brackets, and then anything that's different from the atom you're looking at, you write that after the noble gas. So let's look at phosphorus. We've already done the electron configuration for phosphorus in a previous example. It's in position 3 in the 3p block. So 3p3 would be the highest energy electrons, and anything that comes before it is completely full. So 1s2, 2s2, 2p6, 3s2, 3p3. And for the condensed electron configuration, we look up a row and find neon as the noble gas in the previous period. So we'll put neon in brackets, and then anything that comes after neon, we need to write after it. So 3s2, 3p3 come after neon, and so we need to write those to indicate that it is phosphorus. So this is a full electron configuration for phosphorus and the condensed. Let's look at iron. Iron is in the transition block. It's in position number 6. And remember, that is not one of the exceptions. The exceptions are position number 4, chromium, and position number 9, copper. So because we're here, we can assume that the filling order is normal. So we'll go 1s2, 2s2, we're here, 2p6, 3s2, 3p6, 4s2, 1, 2, 3, 4, 5, 6. So 3d6 would be the full electron configuration for iron. If we want to write the condensed electron configuration, we go up a period and go to the noble gas, that's argon. And anything that comes after argon for iron, we need to write. So 4s2, 3d6 comes after. I haven't yet done an example of an orbital diagram that involves a d sublevel, but remember the rules are going to be the same as they are for the ones we've done before. We're going to put one box for each s sublevel, including the 4s, and then how many boxes do you remember you put for a d sublevel? For s it's 1, for p it's 3, for d it's 5 boxes because there are 5 possible orbitals that we can put electrons into. 2 in each represents 10 electrons. Then we need to fill them up. So 1s to 4s are completely filled, so 2 electrons in each, 1 up arrow, 1 down arrow. With this D block, it's not completely full. There are only 6 electrons, but there's space for 6. And so we have to follow Hund's rule to make sure that we fill the electrons correctly. And so I like to do all up arrows first. So 1, 2, 3, 4, 5. And we need to put 6, so we'll go back around and put that 6th one in that first block. So this is the correct orbital diagram for iron. The last example here is bromine. So we'll go find bromine. It's right here. And it's in the P block of period 4, meaning its highest energy electrons are 4p5. Everything that comes before 4p5 must be completely filled with electrons. There's no exceptions to the rule for the S and P blocks, so we can fill it like normal. 1s2, 2s2, 2p6, 3s2, 4p6, 3p6, 4s2, 3d10, 4p5 to indicate that it's bromine. And for the condensed electron configuration, you're going to take argon. It's the noble gas in the previous period. It's always the one in the previous period. Put it in brackets, and then anything that's different between argon and bromine, you're going to write after that. And so the 4s2, 3d10, 4p5. And I'm going to indicate to you, so here's what I had just said. This is the correct one. You may also see this electron configuration right here, this condensed electron configuration, argon 4s2, 4p5. There is a specific reason for it, and I wanted to just bring it up in case you see it and are confused by it. And so when we're writing these condensed electron configurations, we're often trying to represent the electrons that are going to participate in chemical bonding, and those are going to be your highest energy electrons. So bromine has 7 valence electrons, and so sometimes we'll write the condensed electron configuration this way to represent those 7 valence electrons. However, this one right here is correct, and you guys are welcome to use this version instead because that makes the most sense logically. I am fine with either method. I just wanted you to be aware that you may see both. Elements within the same group tend to have similar reactivities to one another, and we have special names for a lot of those groups, like the alkali metals, the alkaline earth metals, the halogens. And the reason for this is because they have similar electron configurations, or at least their highest energy level has a very similar electron configuration. Take the alkali metals, for example. Lithium, if you look at its condensed electron configuration here, has 1 electron in the 2s subshell. Sodium has 1 electron in the 3s subshell. And if you keep going down, you would find that potassium has 1 electron in the 4s subshell. So they all have 1 electron in their highest energy level. And that has a lot to do with the reason that alkali metals tend to give away 1 electron when they form ions and when they participate in chemical reactions. And so if you click on the picture here, I'm not going to do it for the sake of the video, there's a link here to look at how alkali metals react with water and displace hydrogen. The video is specifically for the reaction with potassium and water, which is very entertaining and explosive. And one thing you'll know is that as you go down the group, the reactivity tends to get higher. And that's because where the electron is, it's in the higher energy level, so it's easier to react. And the takeaway from this slide is that elements that are in the same group have similar electron configurations. They essentially just differ in the energy level where those electrons are. And that is why they have similar chemical behavior and similar reactivities. And so that brings us to the concept of which electrons are reacting and which ones are not reacting. And so we can categorize the electrons based on where they are in the electron cloud. We have the inner electrons, sometimes called the core electrons. Those are the ones that are not in the outermost energy level. So when I say outermost, I'm talking about the highest energy levels, the furthest from the nucleus. And those are usually the ones that are in common with the noble gas from the previous period. So that's what we often put in brackets when we're writing the condensed electron configuration. They're not going to participate in chemical reactions because generally they're unavailable to. They're too close to the nucleus. The ones that are available for reacting are the ones that are on the outside of the electron cloud. And so essentially we call those the valence electrons. Now valence and outer are not exactly synonyms, but we're not going to go into detail about what the specific difference is between a valence electron and an outer electron. But just know that the valence electrons are the ones that are involved in forming compounds. Those are the ones we tend to care about the most. How many valence electrons does an atom have? How many is it going to give away? How many is it going to accept? With the main group elements, remember the group A elements, the valence electrons and the outer electrons are actually the same thing. And those are represented by the highest S and highest P electrons. For the transition elements, it's just the highest S and the highest D. And so I have this mathematical designation here. If you remember, if a transition element has its highest energy level, if it's in period 4, its highest S energy level is 4S, and its highest D energy level would be 3D. So that's what the N-1 is. And so if we have an element like sulfur, which is a main group element, you would write its electron configuration, and I've highlighted the difference between the inner electrons and the valence electrons. And so the highest energy level for sulfur is energy level 3, and for the main group element, which sulfur is, it's the highest S and the highest P. And so these 2 electrons that are in the S sublevel and these 4 electrons that are in the P sublevel of energy level 3 represent the valence electrons for sulfur. So sulfur has a total of 2 plus 4, 6 valence electrons. All of these ones that come before energy level 3 represent the inner electrons. And if you notice the way we write the condensed electron configuration, we write neon, which is the noble gas that comes before sulfur. Those represent the inner electrons, and then we write the valence electrons after it. Now for a transition element, like iron, you would write its full electron configuration like this. 3p and before represent the inner electrons, so the ones that are not going to participate in chemical reactions. And then its valence electrons are represented by the 4s electrons and 3d. So it actually has a total of 8 valence electrons, but not all 8 of them are going to react. Typically, iron is either going to give away 2 electrons from that 4s subshell, or a total of 3 electrons, where it'll give away these s electrons and then borrow one of the electrons from that d sublevel. And so the inner electrons for iron are 1s through 3p. The valence electrons are the highest S and highest D sublevel. If you're ever asked how many valence electrons does an element have, for the group A elements, it's really easy to determine. The group number corresponds to the number of valence electrons that the atom has. So you can easily use the periodic table to determine that. For chlorine, if I asked you how many valence electrons does chlorine have, you could look and see that chlorine is in group 7, and chlorine has 7 valence electrons. And if you don't believe me, write its electron configuration, and you'll find that, remember the definition of the valence electrons for the main group elements, it's the highest S and highest P. So we've got 2 in the S sublevel, 5 in the P sublevel, 2 plus 5 is 7. And then if you want to know what energy level those valence electrons are in, it's whatever period that element is in. And so chlorine has 7 valence electrons, and those 7 valence electrons are in energy level 3. Chlorine is also in period 3. So let's practice writing the full and condensed electron configurations for the following elements. And we want to identify which ones are inner electrons and which ones are valence electrons for each by first identifying, is it a main group element, and follow those rules, or a transition element and follow those rules. We're also going to write the valence orbital diagram. The only difference between a regular orbital diagram and a valence orbital diagram is for the valence, all we draw the orbital diagrams for are the valence electrons. We don't need to draw all of the inner electrons. All right, so for potassium, hopefully you have a periodic table in front of you. I didn't have enough space on the slide. Potassium is in group 1A and in period 4, so its highest energy electrons would be 4s1. So we've got 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. If you wanted to write the condensed electron configuration, the noble gas that comes before it would be argon, and then we would write 4s1 after it. And when we're identifying the inner electrons and valence electrons, we want to see, is this a main group element or a transition? And you know potassium is a main group element. It's in the S block. And so it's the highest it's the highest energy level in any S and any P sublevels that are in that highest energy level. So in potassium, the highest energy level is 4, and there's only an S sublevel. So the only valence electrons are going to be this 4s electrons. And so everything that comes before that, those are inner electrons. The 4s1, that represents the valence electrons. And you know that potassium's in group 1A, and the valence electrons correspond to the group number. So the fact that we've highlighted one electron for an element in group 1A as the valence electrons makes sense. If you were going to identify them in the condensed electron configuration, remember the noble gas in brackets represents the inner electrons, and then we write the valence electrons after it. And if we were going to draw the valence orbital diagram, we only need to draw the sublevels where there are valence electrons. So that would be the 4s energy level, and we'll put that one electron in there, and it'll be facing up. The next element is copper, and that you would identify as a transition element. And as a transition element, you need to double check for any of those special cases. And if you remember position 4, the chromium group, and position 9, the copper group, those are your special cases. So copper is one of those special cases. So let's remember how to fill them. We have 1s2, 2s2, 2p6, 3s2, 3p6. Now we get to the special case. Remember with the special cases, there's one electron in the S sublevel, so it's going to be 4s1, and then copper's in position 9, but we need to add one more electron to make 3d10. So this is the full electron configuration for copper. We would write the condensed, the noble gas that comes before it as argon, and we write 4s1 3d10. And then for the inner and valence electrons, remember for the valence electrons for copper, it's the highest S energy level and then the D energy level that follows it. So the 4s1 and 3d10 would represent the valence electrons. So 3p6 and before represents the inner electrons. For the valence orbital diagrams, we'll draw the 4s sublevel and 3d sublevels, and then fill them. We'll put one up arrow in 4s, and then in 3d, we're going to completely fill it with electrons. So one up arrow and down arrow in each box, each of the 5 boxes. All right, bromine. Bromine is in group 7A, and it's in period 4. It's in position number 5. And so the highest energy electrons are going to be the 4p5 electrons. And so we need to fill any sublevel that comes before that. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10 is completely full, and then 4p5. And then for the condensed electron configuration, remember we talked about that a little bit. With bromine, for the inner electrons, this is a main group element, and so the highest energy level is energy level 4. And so remember, when we're identifying the valence electrons for a main group element, it's the highest energy level and any s and p sublevels that are in that energy level. So the valence electrons in this case are going to be the 4s2 and the 4p5 only. And now you can see that those 2 electrons in 4s and 5 electrons in 4p, 5 plus 2 is 7, and that corresponds to the number of valence electrons we should have for an element that's in group 7a. Those d electrons are actually inner electrons. For an element like bromine, those will not participate in chemical reactions. And so that's why sometimes we write the condensed electron configuration omitting the 3d. Remember, I'm not particular about whether or not you write the 3d10 in the condensed electron configuration. You can either keep it in or leave it out. So for the valence orbital diagram, technically you should only be drawing the s and the p, the 4s and the 4p. And so we'll put 2 electrons in the 4s and then distribute the 5 electrons in 4p appropriately, which should look like this. All right, so far we've only talked about electron configurations for neutral atoms, but we can also write electron configurations for ions. We know that atoms form ions by either giving away electrons, and they become cations when they give away electrons and have a positive charge, or the atom can gain electrons, and when it does, it forms an anion, and it has a negative charge. And so atoms are going to form ions in specific ways. We know that metals like to give away electrons, and nonmetals like to accept electrons. And the reason for this is because they are trying to attain the electron configuration of the nearest noble gas. And it's usually more energetically favorable for metals to form cations because they can get to a noble gas easier or spend less energy to do so by giving away some electrons. And for nonmetals, it's easier to get to a noble gas configuration by gaining electrons. And so that's why nonmetals tend to form anions. And so the reason they're trying to obtain this noble gas configuration is because it's more stable, or it's in a state of lower energy. Remember, energy is driving pretty much everything about chemical reactions. And so let's look at an element like sodium, which we know is an element that tends to form a cation because it's a metal. It's in group 1a, so it's an alkali metal. And if we look at the electron configuration for a neutral sodium atom, so it hasn't lost or gained anything, we would have 1s2, 2s2, 2p6, 3s1. And I've highlighted that 3s1 electron as the valence electron. And here's the condensed electron configuration for comparison. And so what we know about alkali metals is that they like to give away 1 electron when they form an ion. Well, the 1 electron that they give away is that valence electron. It's the outermost electron, and it's going to be furthest from the nucleus, so it's going to be the easiest to remove. And so the reason the alkali metals like to give away 1 electron is because they have 1 valence electron. And so sodium loses that 1 electron to form the sodium ion, and when it gets rid of that 1 electron, it has the electron configuration 1s2, 2s2, 2p6, which is the same as the electron configuration for the noble gas neon. For an element like magnesium, another metal, we know that it likes to lose 2 electrons to form the magnesium ion. And if we look at the electron configuration, we can see why that is. So here is the electron configuration for a neutral magnesium atom, so it has not become an ion yet. We have these highest energy electrons, the 3s2 energy level. When it loses 2 electrons, it loses those 3s2 electrons, so the valence electrons in magnesium. When it does that, it has the electron configuration 1s2, 2s2, 2p6, which is the electron configuration of the noble gas neon. So the reason magnesium gives away 2 electrons, and the reason that all of the alkaline earth metals give away 2 electrons, is because they can obtain the noble gas configuration of the element in the previous period. That's the easiest way for those metals, those elements, to achieve a noble gas configuration. Well, what about for nonmetals, or things that generally like to form anions? Well, if we take fluorine, for example, fluorine has the electron configuration 1s2, 2s2, 2p5. It has 7 valence electrons. And if it wants to obtain a noble gas configuration, it has 2 options. It can give away all 7 of these electrons to have the same noble gas configuration as helium, so give away 7 electrons, or If it adds just one electron, it can fill this 2p sublevel. And when it fills the 2p sublevel, it's going to have the same electron configuration as the noble gas neon, which is directly to the right. And so fluorine prefers to gain one electron to form the fluoride ion. When it does that, it has the electron configuration that is exactly the same of that as neon. And so it's much easier for nonmetals to accept electrons, specifically for fluorine to accept one electron, than to give away 7 electrons. What about an element like sulfur, another nonmetal? Sulfur is in group 6A. It has 6 valence electrons. And so if sulfur wants to obtain a noble gas configuration, it's got 2 options. It can give away 6 electrons, or it can gain 2. And so when sulfur participates in chemical reactions, it will often gain 2 electrons to form the sulfide ion. It'll put those 2 electrons in that 3p sublevel to fill it up, to make it 3p6. And when it does that, it has the same noble gas configuration as argon. And so in general, anions are going to achieve the noble gas configuration of the element that's in the same period, so the one that's immediately to the right of it. So let's do some examples in predicting what the most likely monatomic ion is. This is something you probably already know how to do, but now you can more clearly see why some of these elements form the ions that they do. So we're going to write the both full and condensed electron configuration for the neutral atom and the ion that's going to form. So for the oxygen atom, here's oxygen right here. It's in the P block in energy level 2 in position number 4. So 2p4 will be the highest electrons. So we have 1s2, 2s2, 2p4. And the condensed electron configuration, we have helium, 2s2, 2p4. And so when we think about the ion that oxygen is likely to form, think about what we just talked about. We know it's a nonmetal, and it's trying to get to a noble gas configuration. So it either has 2 options. It can lose 6 electrons. If it loses 6, it has the same electron configuration as helium. Or it can gain 2 to have the same electron configuration as neon. And so oxygen strongly prefers to gain 2 electrons. And so that would make it an anion, O2-. And so when we gain 2 electrons, or when oxygen gains 2 electrons, where does it put those? In that p sublevel. There is only 4 in the neutral atom, and when we add 2, there will be 6. So 1s2, 2s2, 2p6. Or you can write the condensed electron configuration. I'm not specific about which way you write it. You can either just put neon in brackets to indicate that it has the same electron configuration as neon. I've also seen Alex write it like this: helium 2s2, 2p6. So if you start at helium 2s2, 2p6, that's the same as saying neon. All right, next let's look at the rubidium atom, which is one you're probably not as familiar with. Here we can find rubidium in the 5s1 sublevel, so that means that everything that comes before it in a neutral rubidium atom is going to be completely filled with electrons. So we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s1. And so now you can see why condensed electron configurations are highly desirable. Writing the condensed electron configuration is much easier. We put krypton in brackets and put 5s1 after it. All right, so let's think about the most likely monatomic ion that rubidium is going to form. Is it going to give away electrons or accept them? And if it wants to obtain a noble gas configuration, it can either gain a whole bunch of electrons to become xenon, or it can just give away 1 and be like krypton. And so obviously rubidium is going to give away the 1 electron. And you also already know that the alkali metals, which rubidium is a part of, like to give away 1 electron to form a positive 1 cation. And so we're going to get Rb plus 1. So which electron is it going to give away? That highest energy electron, that 5s1, the valence electron. And so we can write the full electron configuration. The only difference between the atom and the ion is we omit that 5s1 electron. And then for the condensed electron configuration, I prefer to just write the noble gas that it becomes, krypton. All right, so here's an Alex example interpreting the electron configuration. In some of these examples, they'll give you a neutral atom, and some of these examples are going to give you an ion. in the noble gas configuration. And so it's really important to read what they have to say because that is going to tell you how to do the example. And so in this case, we have an atomic cation. So think about that, what that means. It's an element that has given away electrons to obtain a positive charge, in this case specifically a positive 3 charge. And then the ions electron configuration, it's in the noble gas notation, helium 2s2 2p6. And so we need to identify the chemical symbol for the ion. So we want to write the symbol and the charge that it has. The symbol is going to be the hard part. The charge is given to us. We know it's something that's going to have a positive 3 charge. So let's figure out what element it's talking about. So find the atom that is represented by the electron that is given to you. We have neon, because we have helium 2s2 2p6, so helium 2s2 2p6. So we're here at neon. And we know that it's a cation, which is +3, meaning the atom has lost 3 electrons already. And so if it's lost 3 electrons, what we need to do is add 3 electrons to neon, or add 3 spaces to neon to figure out which element it is. So if we go 1, 2, 3, that represents the element aluminum. And so this electron configuration is aluminum with a 3+ charge. Next, it wants to know how many electrons the ion has. Not how many it's given away, not how many it started with, but how many does the ion currently have? Well, aluminum had 13 electrons in the neutral state, but when it made the cation, it gave away 3 of those electrons, so it has 10 total electrons. Or you could have started at neon and know that neon had 10. That would have gotten you there as well. Next, how many 2p electrons? These questions are very straightforward. You can just look at the electron configuration, 2p6, that 6 right there tells you exactly how many 2p electrons there are. The remainder of the chapter is going to appear in a separate video where we talk about the trends in different atomic properties.